Welcome back, everybody. This video will cover the lecture notes from section 6.3, and just a note before we begin, this course covers 6.3 before 6.1, so you should have just viewed the videos for 5.3, and then we move right into 6.3, and then we jump to 6.1 and then 6.4. Alright, so we're changing our focus to integrations, sometimes also known as the antiderivative or integral. So in chapter 6 we change our focus from derivatives to the antiderivative or the integral, and so we'll explore what exactly that means, and we'll start with an example we all probably know very well, which is using rate of change of a vehicle. So, or maybe you're on a bus or in a car and you're moving at some constant speed. Let's say we're driving 60 miles an hour south for 4 hours. And so if we were to plot that function velocity over time in hours, then we would get the plot below. And if we considered how far we've traveled, then we would all immediately say that we've covered 240 miles. That, of course, comes from the fact that we were moving at a constant 60 miles per hour for 4 hours. And so we multiply that and we can include our units and see that the hours will cancel and we're left with 240 miles. And the area of this rectangular region corresponds to the 240 because on one axis we have a length of 60 miles per hour, and on the other side length we have our 4 hours. And so this area that's shaded represents our change in distance, and so that will be an important point of this section. So that actually answers question 2. The graphical representation of this distance is the area under the curve. So if we have any velocity curve, the area under the curve represents our net change in distance over that time period. Typically our velocity is not constant, and so you can imagine, let's now suppose for the next 2 hours we were stuck in some traffic and we only traveled at 40 miles an hour, and so that would be represented by this piecewise function here. After 6 hours we can still understand our change in distance as the area under the curve. So putting that all together, we've traveled at 60 miles an hour for 4 hours and 40 miles an hour for 2 hours. So this gives us 240 miles plus an additional 80 miles for a net change in distance of 320 miles. So we're taking advantage of the fact that the area under the curve still represents our net change in distance and that geometric areas add. So we can just find the areas of each of these individual pieces and add them up. Unfortunately, in the real world, what information typically looks like when we collect data is that it's nonlinear. So it's non-piecewise and it's all sorts of has all sorts of undulations. So when we have real-world data, generally the case is that it's nonlinear. And so the ideas that we used above don't quite work. However, they are useful for approximating the area under the curve. So this plot, we could still use the area of rectangles because those represent distance. And so we can approximate our net change in distance by approximating the area under the curve using rectangles. So question 4 asks us to use area of rectangles to estimate the distance traveled over 6 hours, and it asks us to sketch the rectangles in the figure above and determine whether our estimate is an overestimate, underestimate, or undecidable. So we could do this in a number of ways, but let's just try to fill in the area as best as possible using a few different rectangles. So I'm just going to suggest one way to do it, and you may come up with another way, so try your own way, and then you can think about what your area should be by taking the areas of each rectangle, multiplying the sides to get those areas, and then adding them up. So there we go for the calculation, and you can see that I've grouped together all of these first rectangles that I drew had a height of 60, so I grouped that whole chunk into one rectangle of width 4 hours and height 60 miles per hour, and then my second term is the height of 40 miles per hour times the distance of 1 hour or length of 1 hour rather, and the last one is a height of 60 miles per hour times a length of 1 hour. So adding those all up, you should get 340 miles. So just a few sentences to summarize our results. So as you can imagine, we could all come up with many different ways to go about estimating the area under the curve. And fortunately, there has been a way that's been developed called the left and right Riemann sum, and it's a way for us to consistently come up with an estimate for areas under the curve, and it allows us to refine our estimate as much as we wish. And what we're going to see is that this actually allows us, when paired with the limit, to move from an approximate area under the curve to exact area under a curve. So that's our main motivation for wanting to formalize a way to rigorously estimate areas under the curve. So these pictures here are a couple of examples of left and right hand sums. So the image on the left is a left hand sum, and the image on the right is a right hand sum. So the dotted red line is the actual function, and the shaded blue area is our estimate of the area under the curve. And those heights of the rectangles, this is called a left-hand sum because the heights of the rectangles come from the function value at the left endpoint of each subinterval. So starting at the left from 0 to 2, the height of the first rectangle is this value of the function at x equals 0, and that is a height of 0. So there's no rectangle there. And moving on, we see that the next interval from 2 to 4, the height comes from the left endpoint here, and that function value has that height. You can estimate it, but we don't need to do that in this case. And so that's where that shaded region is coming from, is that height. And so you just kind of sweep along from left to right and draw the heights of those rectangles using the left endpoint of each subinterval. Similarly, the right-hand sum comes from taking the rectangle heights to be the function value at the right-hand side of each endpoint. So it doesn't matter which direction you start from. For the right-hand sum, sometimes people like to start from the right-hand side. So let's do that. Our first subinterval is here from 8 to 10, and we're going to, the right-hand endpoint is 10. So if you look up, the height of the function is there, and so that gives us the height of this rectangle. And you just draw a line over and down to the end of your subinterval. From 6 to 8, we're going to choose the right endpoint, so the function value is there, and similarly, that's where those rectangles are coming from. So we'll draw a few of our own in the upcoming problems. So this box below gives us the mathematical definition of the left Riemann sum, or left-hand sum, and right Riemann sum, and that's what we just discussed with those images. You don't need to memorize this formula, but this is just saying that the left-hand sum is a sum. That's what this notation means, here and here. So both the left and right-hand sums are sums of rectangles. So each of these terms are the areas of each individual rectangle. So this being the height of one of the rectangles, and delta x meaning the change in our width. So this is our width. So this is just the mathematical formulation. And as I mentioned, you don't need to memorize this because we'll discuss how this all works and how you can calculate left and right-hand sums for any function. So looking at this example, you'll see these problems always have to tell you to determine a left or right-hand sum of a certain function. So here we have LHS, which means left-hand sum of this function, g of x. So we need a function, either an image like we have here, a plot, or the algebraic function. We need to know where we're taking these rectangles. So what interval, it might be the whole domain, or in this case, you can see it's just 1 to 3. So always mark that first and foremost so that you can keep your drawing where it needs to be. And then we need to know either how many rectangles or the width of each rectangle. So in this case, we're given n, and whenever you see that, know that n is representing the number of rectangles. So we want to fit 4 rectangles into this interval from 1 to 3. And one of the assumptions that we will make is that all rectangles will have equal width. And there are several reasons for that. It comes from the definition above, the formal mathematical definition, but for our purposes, we just need to know this fact and know how to use it. So what we're working with is an interval width from 1 to 3. So the length of our interval is going to be found by subtracting the endpoints, so 3 minus 1. And you see I've written delta x on the left-hand side. Delta x will always represent the width of our rectangle. So we'll need to calculate that because we want to fit 4 rectangles of equal size into this interval, so we need to know how wide we should draw them. So we take the length of our interval in the numerator and we need to break that into 4 equal sized pieces, so we divide by n, or in this case 4, and this will give us a half in this example. So that tells us the width of each of our rectangles should be a half, and now we can go to our diagram and skip count by 1/2. So if the ticks aren't there, just go ahead and fill those in. So at 1, at 3 halves, at 5 halves, and we're all set. So those are our ticks, and if you don't like fractions, go ahead and use decimals. Now we're ready to draw our rectangles. So you can always check by just kind of drawing the base of the rectangles, and we should have 1, 2, 3, 4 of them. So that's looking good. That tells us our width must have been correct as long as we skip counted correctly. So how do we know which height to draw? That comes from our left-hand sum. So starting on the left-hand side, we look at each subinterval. So we're looking in this first example from 1 to 1.5 or 3 halves. And the left-hand sum says that our height should come from the height of the function using the left endpoint. So the left endpoint is 1, and so we find the function value, and that is the height of that rectangle. So draw the line over and down once you hit 3 halves. The next interval will be from 3 halves to 2, and the left endpoint function value is indicated here at about 1 3/4. So that is the height for the next rectangle, and so on. From 2 to 5 halves, the height is at about 2. So we draw over and down. And lastly, the height is about, again, 1 3/4, so over and down. So given the plot of a function like this and the information about the interval and the number of rectangles, we can draw a left or right-hand sum. So our left-hand sum then will be the sum of the areas of these rectangles. So that was the whole reason we were going about drawing this picture in the first place. So now all we need to do is, once we have the diagram, add all of these areas up. So there we have it, and of course you need to estimate those heights. So I included some extra ticks that I drew in on the y-axis, and then you can see in parentheses the area of each rectangle. So 1 times 1/2 is coming from this rectangle indicated here, and so on as we go. So you should have 4 terms in your sum, and within each of those summons you should have a product representing the area of each individual rectangle. So why don't you go ahead and pause and try this one on your own, and I'll fill in the details. So there you have it. Hopefully your work agrees with this. Just real quick, the first thing was to calculate the width of each rectangle. So you can see here delta x is, our width is 0 to 4. So on the numerator we have that distance, 4 minus 0. And then we wanted to break this into 8 rectangles because in this case n is equal to 8. So we took that length of 4, divided it into 8 equal pieces, which gave us a width of 1/2 for each piece. And then we wanted a right-hand sum. So we take each subinterval, and the height of a rectangle comes from the function value at the right endpoint. So just looking at one of these subintervals, just to make sure it's making sense, let's say from 3.5 to 4. The right endpoint is 4, and so the height there is this value, almost 6, and so that gives us that height of that rectangle. So once you have those rectangles drawn, then the rest of the work is just to calculate the areas of each rectangle and add them up, and so that's what we've done here. Since each area has a width of 1/2, we factored that 1/2 out to speed up the calculation. So your approximation may be slightly different because, after all, we're approximating different heights based on our sketch. So the next problem asks the same question, but instead of giving us a plot, it gives us a algebraic function. And that's okay. We can actually still use the same technique we used above, but we can actually get a more exact answer because we don't have to estimate heights. We can find the exact heights using the function that's given. So we've went ahead and plotted a sketch of the function. Go ahead and try this on your own, and I will provide the details right now. So your width of your rectangles should be the length of the interval, so that's 2 minus -2, or 4, divided by the number of pieces. In this case, n is equal to 4, so we divide that by 4 and see that our width should be 1. So if we start at the left end point of our interval, -2, and skip count by 1, that gives us the base of each rectangle. From here, we use the fact that we're asked to find a left-hand sum to sketch those rectangles. And that is a nice way to illustrate which values of g we need to calculate. So we see that we need for our heights g of -2, g of -1, g of 0, and g of 1. Putting it all together, we get the following left-hand sum. So remember, these terms g of -2 and g of -1 and so on are just the function values at those values of x. So you'll just plug them into the given function x squared, and that will give you those values. So you can see the next question is very similar. We're dealing with a right-hand sum now. So go ahead and try that with this function and see how you do. So there we have it. You can see the width calculation comes from taking the difference of the endpoints as usual, divided by 5 rectangles in this case because n is 5, and then we want a right-hand sum. And so you can see the 5 rectangle area calculations in our work here. And there's no diagram that in this work because you technically don't need a diagram for these problems. However, when you're first approaching these problems, diagrams are extremely helpful. So I encourage you, if you weren't able to calculate this one without a diagram, to sketch the diagram and sketch the rectangles, and that gives you a really strong indication of what you're trying to calculate. So the next set of questions just has you going through and practicing. So these are practice problems, so go ahead and try these on your own, and I'll fill these in the annotated notes, and you can check out the solutions there. Alright, so those are in the annotated notes that can be found in your student portal, so you can access those at any time, just a reminder. And if you have any questions about these, then definitely go back and look at those examples above, but it's really much the same. Get a good diagram based on the information that's given, and then once you have your rectangles, you'll go ahead and calculate the area of each rectangle and add them up. So generally what you'll use in this course is, if you need to estimate the area under a curve, will be a left or a right-hand sum as we discussed above. However, there are some functions like piecewise linear functions where we can actually do a little bit better and find the exact area under the curve just using geometric formulas. So you can see in this example that this function f of x is piecewise linear, and so if we wanted to calculate the area under the curve, we could do so by breaking this up into several regions that are whose area is just areas of rectangles and triangles. And let's actually label these regions A, B, and so on. So there we have them labeled A, B, C, and D, and so we can calculate those subregions using area formulas for triangles and rectangles. And you may wonder why we didn't include this area from 0 to 1, and that's because our interval is from 1 to 5. So let's go ahead now and add up those areas. So there you have it. We've just used areas of rectangles. So for region A, that is a triangle, so we need the triangle formula, 1/2 the base times height. And then region B is just a rectangle, so width times length, or length times width. C, again, another rectangle, as well as D. And so there's an important note that any area below the x-axis, so you're always, when you're sketching areas between the curve or under the curve, we always fill in that area between the function and the x or t axis. So in this case, we fill in that region D, and any area that sitting below the x-axis is considered a signed area, and that is just another way to say that we should always subtract that from the total. So putting it all together, we get that the area under the curve is 3. So this last question is for you to get some practice, so go ahead and apply that same technique using this interval and find the exact area under the curve. So there you have it, and you could break this up in several ways, but we're going from -2 to 5, and so I broke this up into 2 triangles and a rectangle, regions A, B, and C, and so just using those formulas, we get a final answer. So that finishes this lesson, and we'll talk more about this in the second video for this section.